So today we're going to actually start about some of the communication, talking about some of the communication protocols that we previously discussed. So this is going to be stuff like the serial that we've used a little bit, the I2C that we have mentioned a few times, and the other one is the SPI protocol. And then in the activity, what we're actually going to do is we're going to hook up two Arduinos to each other, and we're going to basically have them talk to each other over the SPI protocol. All right, so here is sort of just the generic view of a serial interface, right? We have two different devices. We may have multiple data lines, and we may have some control or clock lines that go with it. And, you know, this is sort of the most general case, and everything else will be, you know, like a specific implementation of this. So it can be what's called asynchronous, which means you basically just have the data lines. And in that case, you know, each device is going to have its own clock to keep its timing. There may be some like handshaking lines. This is the sort of stuff in what's called a UART protocol. But alternatively, some versions are going to be called what's a synchronous serial interface. And those are going to be the ones that have a separate clock line. And one of the devices, usually referred to as the master device, is going to be generating a clock signal similar to the clock pulse signal that we talked about on Tuesday. And what you do is you will transfer a single bit on each one of those clock cycles. This is the sort of alternative you have to a serial interface, where you have a whole bunch of parallel data lines, right? That's why it's called a parallel interface, as opposed to this one here, where you basically only have a single data line for a single direction. In this case, we have a in and out, but those are basically two different lines for the data going either from device 1 to device 2, and the other one would be for device 2 to device 1. And the reason this is called serial is you have to send all of the data one bit after another, right? You have to send it in series, serially. Whereas in this case, you have multiple different data lines. So in this case, all of these data lines are going from either device 1 to device 2 or the reverse, right? And the point is that every single one, you can send, you know, multiple bits at the same time in parallel with each other. That's why it's called a parallel interface. So these lines can either be one-way or two-way, you know, and what we call this is a data bus, and the width of the data bus is how many different lines you have. So in this case, you would have, since we have 8 different data lines, we have 0 through 7, right? That would be an 8-bit data bus, wide data bus, or a single byte wide, right? So that means that basically you can send a single byte worth on every clock cycle. And in this case, you know, your clock cycle might be down here on these control lines, and then you would maybe have another line where you're selecting each device with something called a chip select pin. So one thing to note about doing serial communications on the Arduino, on any Arduino, is that you can basically do these communications in 2 modes, what's either called a hardware or a software mode. right? And hardware mode is when there's actual capabilities built into those pins. That's why we refer to, you know, those certain transmit and receive pins as the serial pins, because there's specific hardware attached to those circuitry on the microcontroller attached to those pins. Alternatively, you could implement it entirely in software, where basically your program is manually flipping pins up and down. You are manually watching what the status of the pin is and watching for it to change. But as you can imagine, that sort of ties up your program the entire time. And because you're having to do this all in a software level rather than having specific hardware designed for this, that's going to be a lot slower. But the advantage of software implementations of these protocols is that you can that means you can implement it on basically almost any one of the pins, as opposed to the pins that have that specific hardware built onto them. In general, your base Arduino libraries, which are, you know, the serial 1, serial 2, serial 3 that we've used in the past, the wire library, which is for I2C that we're going to talk about today, and the SPI library, those are in general going to use the hardware pins. Now, there will be other libraries that will do software implementation of those pins, and they're usually just called software serial or software SPI or software I2C. But like I said, we want, if possible, we want to use the hardware pins because they have actual design capabilities. It'll be faster. It'll be easier to actually get to work. So we've said this before, but we're going to keep saying it, right? You have specific pins that support your UART, which is your serial. Even though all of these protocols are technically serial protocols, when you are talking about the serial pins and serial ports on the Arduino, you are talking about UART pins, the ones that are like the USB. There's also the SPI pins that we've talked about and the I2C pins on certain pins. So in particular, the Mega has 4 sets of these UARTs here. That's the serial 1, serial 2, and serial 3. And then you really only have 1 set for SPI and I2C. But those are your hardware serial protocols on those pins. When you look at the pinout and it says SPI or I2C, it means that there's hardware on those pins. What that means sort of as far as what's the actual hardware, there's going to be, you know, triggers on those pins that will see, like when a clock pulse or a data pulse happens on one of those pins, and that'll trigger the microcontroller to do something. It can jump outside of the program to go handle that. That's what's called an interrupt. And then there's usually separate small bits of memory called buffers, so that basically the microcontroller can copy the data that's coming in into these temporary buffers and hold it for a little bit until your program gets a chance to go look at it and copy the data out of that. And what this means is your program can be doing other things. You can be doing calculations, you can be doing communications on other pins, but because the hardware level in the microcontroller can sort of handle this little bit of data on its own without you checking on it, you don't have to actively be watching the port to get the data. Whereas if I was in a serial or a software mode, I would basically have to go look and be waiting to catch the data, if you will, when it got transmitted. And if I wasn't actively listening to those pins when the data was sent, I would lose it. But those buffers that you're sticking the data in are really, they're not large. They're, maybe 1 or 2 bytes worth. So in general, you need to copy that data out of those buffers relatively quickly, quickly meaning faster than the new data is being sent, so that it doesn't get overwritten and you don't lose it. So as I mentioned earlier, there's 2 basic modes having to do with whether or not you have a clock, and that's called synchronous and asynchronous. So a synchronous mode means that there's a synchronizing signal between the two, which means you have a clock signal that's keeping the 2 devices in sync. Asynchronous means that there is no clock signal, but you still basically need to have some sort of standardized rate between the 2. And what is actually happening is each device has their own clock, and they're basically, on the count of 10, I'm going to send my next data, sort of thing. That's actually what that baud rate setting with the serial library that we've been using does. You're setting what is the rate between individual bits of a transmission. So the serial pins, which are also the UART pins, are pins 0 and 1. That's the regular serial. And then 14, 15, 16, 17, 18, 19, right? If you look at that, that's your TX, RX 1, 2, and 3. That's your serial 1, 2, and 3. Now, the disadvantage of this mode is because each device has to keep its own clock, and none of your clocks are perfect. You're going to have to occasionally basically, reset on when is the beginning of a transmission, right? And this is going to lead to a slower data rate, because you basically have to periodically check with the other device and make sure you're still synced up. So the way that this works, and this is, for example, your actual serial, i.e. the UARTs, is you have a signal like this, right, on the bottom. So you can see on the green hash marks here, that is basically the spacing set by your baud rate. So you've set a particular baud rate where this is the first bit, this is the second bit, etc. Each one of the devices is counting like that. So you'll have what's called this starting signal, or a start bit, so that whichever device is starting the transmission, it'll do that, and that'll signal to the other device that it needs to start counting its based on its clock rate. And then after that, you'll start sending the bits. In this particular case, it's sent from the least significant bit to the most significant bit. So this transmission right here, so in this order, it's 1 1 0 0 1 0 1 0, right? But that's actually sending this particular binary value. So you can see this is an entire byte, and we send it with the lowest bit first, and then we send all 8 bits. And for the UART protocol, which is what the actual serial port, the way that the one that gets sent to your computer, you send data in 8-bit chunks, right? You send a single byte at a time. And in general, this is encoded using the ASCII code. So when I send this particular byte, that's actually the character S, right? And if you look at, and we talked about this a bit in the intro to programming, there's basically a mapping of all of your characters, all of your letter and number characters, and then a bunch of special stuff like the new line and stuff like that, onto integer values. And if there's integer values, you can then, you can get what the binary value is or the hexadecimal value is. So in this case, this is the value for a capital S. It's also a hex 53. So what's the computer is going to interpret this transmission as a character S. So like I said, you start with the start bit, you send your 8 bits, and then you have an ending signal here. And in this particular case, you can see that when the clock is idle, it's up. So I always have to pull this data line low, pulse it briefly low, so that the other device knows to start counting and that I'm going to send something. So we've used a few of these, but mainly print and print line. But these are all the other functions that you can actually use on those serial objects. So you guys are familiar with print and print line, but obviously I can also read on the serial line. And then, I can there's a bunch of different versions of reading where I read a certain number of bytes, or I keep reading until I get a certain character. Flushing is going to immediately transmit whatever's in the hardware buffer. We're not going to get into any of this today, but if you are interested in what these functions do, you would want to look at the Arduino serial reference, and it'll explain how these are used and what arguments you need. But mainly what we're going to use here is just the print and the print line. And the difference between those is print just prints whatever characters, print line prints whatever characters, and then adds a new line at the end. So you skip down to another line. So like we said, we have the regular serial on 0 and 1, and then these are the other 3 serial pins. So there's pin 0 and 1, and that is also the one that's connected to your USB as well. So when you are talking to the computer through the USB, you're using, as we've done several times, the regular serial with no number, and that's also on hardware pins 0 and 1. And in theory, you could talk to your computer through one of these sets of pins, but you would need an adapter that would basically connect those pins to the appropriate USB pins. Because only the serial 0 is connected to the built-in adapter on the Mega. So the other type of serial communications or input-output is the synchronous serial. And what makes it synchronous is that it has a clock line. So in this case, for the Arduino Mega, all of these lines are going to use 5-volt TTL logic. So as long as you are talking to other devices that use that same logic levels, or like another Arduino or something else that works on 5 volts, you don't need any sort of level shifter. But you may actually use like 3.3 volt. There's other Arduino boards that use 3.3 volt logic. And so in that case, you still can talk to each other, but you have to have some sort of logic level shifter or what's called a line driver or receiver. These are all sort of synonyms for integrated circuits that do the same sort of thing. Some of these protocols for synchronous serial, and the two main synchronous serial that, or the two synchronous serial protocols we're going to talk about are SPI and I2C. So they can either have a single bidirectional data line, right? Where I can send data, that's what this example on the right is. I can send data from the mega to this integrated circuit, or back from the integrated circuit to the mega, all on a single data line. But that means that only one of them can be transmitting at once. The other one has to be listening. Alternatively, you can have unidirectional lines where we have a dedicated line that goes from the Arduino to the integrated circuit, and then a separate line from the integrated circuit back to the Arduino. In both cases, you're only going to have one clock line, because the clock line is to synchronize both of them. And in both cases, it's the mega that's going to be generating that clock signal. So the first protocol that we're going to talk about, and this is going to be one that you'll actually use with your payloads in the spring, is called the I2C, or the I2C protocol. So that stands for inter-integrated circuit. So there's two I's and the C. So it's either I2C is what I prefer, but you'll also maybe hear it referred to as I2C, right? With a I raised to the 2 power C. So this is a synchronous serial protocol, because you have a clock line, and it's going to have a bidirectional data line, right? So I only have two lines. I have my serial clock and my serial data. So I can have multiple devices like this, all on the same set of SCL and SDA pins, and that's called a bus, right? These are all connected to each other on the I2C or the I2C bus. So the question then becomes, if all of these devices are on the same, data and clock connections, how does one of them tell that I'm trying to talk to that particular device? Well, the way this works is each one of those separate devices is going to have an address. It's basically going to have a 7-bit number that is the first thing transmitted when you do a communication that tells that device that you're the one that's the one I'm talking to. So the Arduino in this case is going to act like the master device, and it's what's generating the clock. So it will generate a clock signal, and then the next thing that it'll send is this 7-bit address and it'll send that on the data line, so that whichever device I'm trying to talk to knows that it should be listening, and then the other devices will basically ignore whatever is going on the bus. So some of these devices are going to have it entirely hardwired what that 7-bit address is, and you won't be able to change it. So you always want to, you will need to know what the address is for all of the devices you're trying to talk to, because otherwise you can't communicate with them. Some of them will basically have part of the address hardwired, and then they'll have a couple of pins that you can either connect to +5 volts or 0 to set the rest of the address. That gives you a little bit of way to change it. And then there's going to be certain devices like the Arduino that we're going to use as the second device today, where you just set what the address is in software. You basically program the device and you say, this is your address. So you may have noticed on the picture of the bus here, we have two resistors, and which are connected to the +5 volts. And you may recall those are pull-up resistors, right? You need pull-up resistors somewhere on your I2C bus, or it's not going to work properly, right? Remember, we don't want that weird state where we're not connected, right? We always want to have either a positive connection to +5 volts through the resistors in this case, or one of the devices pulling that voltage down. Luckily, the Arduino hardware I2C pins have those pull-up resistors built in, so we don't have to breadboard them or solder some resistors onto that connection. They already exist. So the first thing that you're going to do when you initiate a I2C communication is you're going to send this start sequence. And basically, all of the devices are looking for a specific combination of the data and the clock pin at the same time. And that's what's going to wake them up and trigger them to start watching. So the start sequence is basically you have the data line go from high to low while the clock line is steady at high. Similarly, you have a signal to indicate that you are done transmitting. And in this case, it's just the reverse. The clock line must be high while the data line goes from low to high. So on the I2C, there's basically two kinds of communications that depend on what the master device is trying to do. So the master device, remember, is the one that generates the clock signal. It's the one that's talking to all the other devices. Those other devices are called slave devices because they're doing what the master tells them. So there's going to be two versions of communications, like I said, depending on what the master is trying to do. It will either be doing a read, which is where it's basically asking one of the devices to send it data back to it, or it's going to be a write, where it's going to send data to one of the devices so that they then do something with that data. But any kind of I2C communication is going to be one of these two things. And in both cases, the entire communication can be multiple bytes of data. And in particular on I2C, like the UARTs, all of your transmissions are grouped in sets of 8. So you are sending individual bytes at one byte at a time. Okay, so this is what a write sequence looks like. So this on the bottom is our data line. The other one is our clock line. So if you were to hook up an oscilloscope, you would see something like this. So the first thing that happens is you send the start sequence, right? The data line goes low while the clock is high. Next, you send the 7 bits of the address, right? That's what this A6, A5, A4, A3, A2, A1, A0 is. Then you send a single byte that tells you if it's a read operation or a write operation. And that's why the address is only 7 bytes long, because you're using that last byte as the read-write bit. For a write sequence, that byte is low. For a read sequence, it's high. So if I'm doing a write, I will send the address and then a write bit. I will get an acknowledgement back from the device that from the slave device that will tell me that it is actually receiving. So the master will get here, it'll wait, and then it'll basically look for the other device to ping the data line low on this clock. So the next byte will be a byte of data that will get sent to the slave device that it is going to do something with. Maybe it's going to store that in its memory. This may actually be a command that is going to be interpreted by the slave device. You can also have this set multiple bytes in a row. So I can send the address once and then send a sequence of other bytes of data. That's what I meant when I said a write can have multiple data bytes. After each one of the data bytes, you'll get an acknowledge from the slave, and it'll basically continue like that until there's either a stop or a repeated start, which means I would do this repeated start and then immediately do another data byte. The read sequence is pretty similar. You have start, you send the address, you send a read bit this time. So it's going to be high instead of low. And then the slave device will actually respond with the data. So after the master finishes here, it's going to start listening and wait for this data. And again, you will have acknowledgements and you can have multiple bytes sent like that. So I could be like, this is going to be how you're going to use it often. You're going to ask for a read and then you'll get actual data back from, if this is a sensor, these would correspond to the value that the sensor is reading out. So this is just a more concrete example. If we are trying to do a read on a device with this address, you would send this sequence of bits, right? And then, and then you would send this data here. I mean, I don't think that's particularly helpful without knowing what this device is and what it's supposed to be doing. But that's just sort of to give you the idea. Okay, the library that we're going to use in Arduino to do all of this is called Wire. With a capital W, it's just Wire. So these are the functions we'll actually go into this in today's activity. So you could probably imagine the begin initializes it, reads and writes. You are reading and writing bits. But it's a little bit trickier than that, and we'll get into that when we do the activity. Again, if you always make sure to look at your programming references if you're not sure what the function's doing. So you always want to, and these are built-in Arduino libraries, so you just need to go to the Arduino website and find the appropriate library, and it'll tell you exactly what these do. The other synchronous protocol that we can do on our Megas is called the SPI protocol. So that was developed by Motorola in the 70s. This one is a little bit less standardized than the I2C. All of your I2C devices use that particular timing and work like the examples we showed here. SPI is very more on device to device. In particular, you can set the clock up in 4 different ways. You can set the clock up where it's either idle in the high position, i.e. it's just sitting constantly at 5 volts when it's not ticking, or you can set it when it's idle in the low position. And then you can have the clock trigger on either the rising or the falling edge of the pulse. Remember that on those clock pulses, we either trigger on the rising edge, and the SPI protocol you can set up on either one of these. So if I combine these two modes, high or low, with these two modes, I get 4 total possible combinations. And the way to tell what you're going to need is you basically have to look at the data sheet of the device you're trying to talk to. The other thing about these is, whereas the SP or the I2C, basically every transmission was broken up into individual bytes. The SPI might be weird lengths. It may be like, oh, this transmission will be 13 bits long. However, the way the Arduino libraries work is you basically always are operating in bytes. So if you have one of these weird situations where it doesn't evenly go into a number of bytes, you have to use those bitwise operators that we talked about and like manually shift the bits around and combine them. But that's not something we're really going to get into here. Just something to be aware of if you're trying to use the SPI. Okay, so the SPI is similar to the I2C. You have a master device, and then you have these other slave devices. You have a clock signal that goes from that's generated by the master, and it goes to all of the devices. In this case, though, you have separate unidirectional data lines. I have one line that goes from the MOSI, or from the master to the devices. It's called the MOSI line, and it stands for master output, slave input. MISO is the reverse, master input, slave output. And because of this, you can basically send data both ways at the same time. SPI devices are not going to have addresses like the I2C. Instead, all of these devices are going to have a pin that's called chip select, and you have to pull that pin low to basically wake that device up and tell it that it needs to pay attention to the bus. So consequently, if I have 3 or 4 devices, that means on my Arduino, I have to have 3 or 4 pins that are designated to be the chip selects so that I can pull them low and tell those other devices to pay attention. So like we said, you may, if you're talking to different devices, they may have different logic levels, and that means you may have to do level shifting. So the Arduino Mega, like we said, use a 0 to 5 volt scale. If you've ever heard of or used a Raspberry Pi, that's going to use 3.3 volts, but that doesn't mean that we can't talk to each other. You just have to have a level shifter between those two. And you'll need possibly a bidirectional level shifter or a multi-pin unidirectional level shifter. It's going to depend on which of these protocols you are. So some level shifters will only go one way or the other. Some will be bidirectional, just like the data lines. But all it does is converts the high level on one side to the high level on the other side. Usually your devices are all, the low level is all going to be on a 0 scale, except for the really only common version is what's called RS-232, which is like very old pre-USB serial ports, but is still commonly used. And that's one of those protocols that had a positive 12 volt and negative 12 volt signal for the high and low values. But so, like I said, the level shifter basically converts, on one side, on the input side, you'll have a high, and it'll convert it to the appropriate voltage to be a high on the output side. And these are usually, designed to work with specific voltage ranges and specific, speeds or frequencies, data rates. So if you're using one of these, you want to check out the data sheet and make sure that it's the right version for what you want to do. So that's it for the lecture.